Welcome everyone. Today we are very happy to have Parthiv Haldar from IISC, and he's going to tell us about quantum field theory and Bieberbach conjecture. Over to you, Parthiv.
Yeah, thank you very much for the opportunity. So I will be talking about quantum field conjecture based on recent paper that is going to India and.
Your voice is breaking.
Can't hear you.
Yeah, Parthiv, we can't hear you properly.
Oh, so
Maybe
now you can hear me?
closer to the mouse, to the microphone. Yes.
Yeah. So now can you hear?
Yeah, much better.
Okay. Hang on. Yeah. Okay. So I guess now I'm audible clearly.
Yeah.
So the main question, how to locate theories describing scattering of particles in general quantum field theory, using some basic requirements. So there's some basic physical requirements of unitarity, causality, and locality, etc., etc. So these are the questions. So this question is a decade-old question. It was, it started investigated in 1950s and 60s. Partly to explain strong interaction, because strong interaction at that time there was no viable quantum field theory description, and it was taken up by people like Mandelstam, Bro, Epstein, Glaser, Chu, Martin, and it was Chu who kind of championed this method called bootstrap or S-matrix bootstrap. Now that program didn't go far because of some of the obvious technical obstacles. But recently, the program has been has seen a revival in the modern context. And there are, of course, aided by strong numerics, but recently there are the analytics is also getting revived very recently in the context of effective field theories, and also possibly kind of constraining the theories of quantum gravity. So instead of seeing at the UV part, rather trying to constrain or rather locating the quantum gravity theories by looking at the low energy part of the theory. So to speak, that if there is a UVS metric satisfying this property, what the low energy amplitudes or theory would look like. So obviously, in order to proceed, we need some fresh outlooks and some powerful numerics that can prod the way ahead. So based on this, it is in this context that my talk is going to be. So here's a brief outline. So we'll start with essential something called a crossing-symmetric dispersion relation. We'll then do a little bit of digression into some necessary math that we'll require, which will ultimately aid us, which will ultimately enable us to put some bounds on Wilson coefficients, the EFT expansion. We will also be able to bound amplitudes. We'll also be able to bound the amplitude itself. And finally, we'll give some outlook and what kind of direction that can be explored. Okay, so let's start with what we. So this is kind of the central character, the principal character of our story, which is a crossing symmetric dispersion relation. Now, we will consider scattering of identical massive scalars, and for this talk it's uncharged. So a prototypical example would be neutral pion scattering, pi naught going to pi naught pi naught. Now this has some particular analytic structures. Now usually a lot of these structures were proved using the LSZ axiomatics in 1950s, 60s. I mean, much of the work goes.
Can I ask a question, please?
Yes.
Sorry.
Yes. Yeah.
Is that okay?
Yeah. Please go ahead.
Yeah. I mean, pi naught, actually, there can be many other particles on the right-hand side, right? Like pi naught can decay into 2 gamma and as a famous decay. Some other particles.
Yes.
So then, what is this?
So this is just it's like then kind of an artificial the elastic scattering like of pi naught. I mean, it's in that context they studied these properties.
Okay. Thank you.
So these were proved using the LSZ axiomatic structures at that time, in 50s and 60s. Different works by Boglubov, Mandelstam, Bro-Epstein, Glescher, Martha, and etc., etc. So let us first summarize some of these, review some of these analytic structures which have been proved rigorously in the sense that from the axiomatic structure.
Sorry, Parthiv.
So, yeah.
So now that you are talking about the analytic structure of the amplitude, some information about the analytic structure is also obtained by causality, right?
Yes,
Causality.
Yes, right. So in fact,
so
when
maybe
I told,
you will say,
right. So first is, in fact, the analytic structure that I'm going to talk, what I'm going to talk about is essentially when you talk about analyticity, it essentially follows from causality in this. What is known in the literature called microcausality, which is essentially that at space-like separated points, fields actually commute. And it is by virtue of this you can this plays a central role in proving what is the earliest known thing, that the dispersion relation. So historically, dispersion relation was obviously first came in the context of electromagnetism by the works of the Kramer's chronic, who obviously was studying basically trying to understand how the refractive index of a medium would vary with frequency. It was actually in 50s when people tried to see that whether such a dispersive representation can be obtained for scattering amplitudes, which is the MST. And it was proved, at least for this reaction, rather this scattering process, that is scattering of identical massive scalars, it could be proved that the amplitude actually satisfies fixed transfer dispersion relation in all the three channels. And this is very important, that they could prove that it's actually in all the three channels. So note that the three channels, the physical domain for the three channels are mutually disjoint, so they do not intersect. So when you prove such a dispersion relation, usually you not only prove the dispersion relationship, but it also comes with a certain domain of analyticity. So that brings me to the next part, that each dispersion relationship comes attached with the domain of analyticity where the dispersion relationship is actually valid. Now, as it is the case, for each channel there is a domain of analyticity. Now, obviously, definitely you would have to have that it satisfies in the physical domain. So just to write down, so for S channel, for example, it will be S greater than 4m square and t less than 0, and u accordingly, yes, because S plus t plus u equals to 4m square. But there exists a domain of analyticity, a sort of enlarged domain of analyticity. So this is a domain which is larger than the original domains that have been proved in the three channels, where the amplitude for all the three channels are analytic. So essentially, there is a larger domain which connects all these three physical domains. Because without this crossing symmetric domain, so essentially the statement of crossing symmetry has two parts. One is obviously there has to be a larger domain. There has to be a single domain which contains all the three subdomains, so that you can aid actually the analytic continuation from one channel to another channel. Okay. Another very important part is the so-called Regge boundedness or polynomial boundedness that used to be called in those days. So MST is Regge bounded in all the three channels, such that the fixed transfer dispersion relation can be written, in the respective channel with at most two subtractions. So this was proved by Jean Martin in 1964. So what does it really tells you that MST is, this is small o s square, but what it really tells you, this is less than s square, where you keep t fixed and mod s tends to infinity. But t fixed, it need not be the physical t. It's valid for any t that is within the domain of analyticity. And in fact, it is also true for complex t, which lies within the proving this d is the domain of analyticity, which I will call from time to time the axiomatic domain of analyticity. So this is, in recent times, I think this is being plotted as like chaos bound or something like that. Finally, so I told you about the one aspect, one part of the crossing symmetry, and that is because that is the presence of one enlarged domain which contains all the three domains of the three channels. But there is also,
Sorry, Parthiv.
yeah.
Here you're talking about full quantum scattering matrix, right? Or just the classical?
No, it's a full quantum scattering matrix.
I see. But usually the chaos bound relates to the classical part of the.
I see. Okay. But here it's actually the full. So yeah, in that case, I would say that this is a stronger result because it's a full scattering amplitude, quantum scattering.
Well, it's a different result. Yeah. Okay.
Yeah, different, but yeah. And of course, and there are, so the crossing symmetry has two parts. One is the existence of a crossing symmetric domain, and another is that you can actually analytically continue the amplitudes between. There exists analytic continuation among the three channels, which in this case, in identical scalar, simply reduces to this permutation invariant of, invariance of the amplitude under a permutation of three STU. So essentially, it's an invariance answer S3, which is a symmetric group on three elements.
Sorry, Parthiv, if I may just ask a little bit more about the Szego boundedness. So if you go to previous slide, where does this result? So is this the what they call the Frosta-Martin bound?
Yeah, so this is actually so Frosta-Martin bound actually used to prove this result. Actually, yeah, you need Frosta-Martin bound to prove this thing. So Frosta-Martin bound literally tells you that MST. It's in the forward direction. It goes like lns of this form, but then you need to apply some more structure. I mean, one argument goes like that. Okay, in the S channel there is a bound, and then there will be a similar bound in the U channel by symmetry for fixed dispersion relation. And then these two actually allows you to write down that MST has to be less than S square. So this is by virtue of a theorem called Fragment-Lindelof theorem. But there is another proof where they use the particular nature of the structure, which is called a typical realness. Maybe I will tell towards the last, which allows you to put this bound. But either way, it's yes, you are right. It's related to the Frosta-Martin bound.
So this follows from which physical principles? Because in Einstein gravity, this will not be valid, right? Well, okay. This is classical, I guess. So you will not. Okay, fine.
Yeah. So, since you asked, so this follows from it's some basic. I mean, of course, the first ever proof by Frosta was actually kind of assuming the Mandelstam double spectral representation, but that is not needed ultimately. You can still work with simple just existence of an analytic domain a little bit larger, and unitarity allows you to prove this bound. So unitarity plays a very important role, obviously.
So in this paper, I will be able to find it.
Yes.
Okay.
But just to point out that this is under the assumption that there are no massless exchanges. So I think there are no rigorous theorems like this from the axiomatic literature which proves it for when there are massless particles.
I see. Okay, thanks.
So the crossing symmetric amplitude is, as I told you, is invariant under the symmetric group of three elements. Okay, so now, these are the basic elements which is kind of the starting point. So based on this starting point, now we would like to say something which is known as a crossing symmetric dispersion relation. Now, fixed transfer dispersion relation, which kind of looks like M, of course, ST, but then you fix T, and it's something like S minus S bar or something S bar T. So this looks like this way, but this actually manifestly breaks the crossing symmetry in the sense that your T is now fixed. So it's so essentially you have broken the ST. So in that case, if you want to impose the crossing symmetry, in that case, you would have to do it in a non-trivial way, but it's a difficult task. Now, it would be nice to have a dispersive representation, which is manifestly crossing symmetry. So meaning which will, as you can see, which can have a kernel because essentially it's an integral transform. The kernel will be so you kind of expect or try to obtain a kernel which is manifestly symmetric under S3. Now this can be achieved using what you can call a parametric dispersion representation or dispersive representation, which was first obtained or rather worked out in this old paper by Oberson Curie, so it's a very less known paper, it's a very small citation, which was recently revived in the modern context, applied in the EFT context by this PRL paper by Sina and Zahir and in the Namedullah. So the essential construction consists of writing the dispersion relation on an analytic manifold, which is invariant under S3. And this analytic manifold usually is of the form of a cubic. So it's of the form of like S T of this form. So it is of this form that you write on this manifold. You actually write down the dispersion relation. Now, when you try to write down the dispersion relationship on this manifold, you would like to parameterize ST and U suitably on that. So what we will choose a rational parameterization. So this is a rational parameterization that we are working with. So the rational parameterization is actually to avoid any kind of possible branch points or spurious branch points that may arise purely out of the parameterization problem. So rational parameterization do not lead to that. And there you can so we have kind of rescaled the STU into this S1, S2, S3, and they have been defined in this form there, where ZKs are basically the cube roots of unity. So under this, this Z and A, or rather Z cube and A, they are actually crossing symmetric variables. In particular, they can be expressed in terms of the crossing symmetric combinations of these three S1, S2, S3 in this form.
Sorry, Parthiv. Like I didn't understand your statement that this is done to avoid branch singularities. What do you mean?
Spurious branch singularity. So suppose you have so what you would like to write down is a dispersion. So in the intermediate step, when you derive the crossing symmetric dispersion relationship, you would like to write a dispersion relationship in Z. So that's how you start. And then you do not want to have unphysical branch points, which may arise if you do have a non-rational kind of parameterization.
I see. So the non-analyticity is in Z variable, you mean?
Yeah. So you want to so your expectation is that you should parameterize in this way, that in the Z variable you should not have any extra non-analyticity.
Okay.
So one question, Parthiv. So you're saying this parameterization is for the manifold given by S minus 8, T minus 8, U minus 8 equals K, right?
Yeah.
So to begin with, you had a two-dimensional space of S and T.
Yes.
But with this, it should be one-dimensional, right? But your parameterization is for two-dimensional space. So it confuses.
No, it's so at this stage, of course. So this is here it is. So you have in the sorry. So you have in the problem two variables, ST or so essentially you have C2 in your MST is a function on C2 manifold. But so what you're doing is that you are not so this is not a single manifold. So here A is the parameter. Yeah, so that's I forgot to say. So A is the parameter. So essentially you're foliating your C2 in terms of this, yeah, you're foliating the C2 in terms of this manifolds, and then on each hypersurface you're considering so that A varies as a parameter.
I see. So Z is a good variable on that given slice.
Yes, on a given slice. Yeah.
Thanks.
Right. So
Parthiv, I'm a bit confused. Can you go back to the previous slide, please?
Yeah.
So here S1, S2, S3 are related to ST and U.
Yeah.
And you are parameterizing these three variables
Yes.
in terms of one variable z. So is the
No, there are two variables. So one is z and another is a. So essentially you have two in problem. So a is your.
I see, but a was already there in the
Right. So it's almost like, suppose you are foliating your R3 in terms of spheres. I mean, in terms of spherical surfaces. Now, each leaf will be characterized by a radius of the sphere, and then on each sphere you can consider two variables.
I see.
So here it's almost like that.
Okay, got it. Okay, thank you.
Yeah. Okay. So these are the crossing symmetric combinations. That's how x and y, they are related to z. So under this mapping, what happens is that the physical cuts, which is SK. So recall just to the mu equal to 4m square. 4m. Yeah, mu equal to 4m square. Sorry. Yeah. So the physical cuts, which are STU greater than equal to 4m square, or which is equivalently SK greater than equal to 2 mu 3, they map to sections of unit circle, which are shown in this way. So essentially, these reds are actually that's where the maps are getting cuts are getting away. Now, this is for a particular value of a, which we are considering. Now, what happens is that if you go beyond this value, it can happen that these branch cuts get mapped to the real or within this along the real z-axis within the disk. Now, for our purpose, we do not want that. We just want we just want to exploit. So we do not want any kind of other kind of singularities. Assuming we are not considering any pole, we just want an analyticity within the unit disk, in the interior of the unit disk. The boundary is where we do not we want everything to be there. So in order to maintain that, in order to keep that in our radar, we are considering A to be lying in this region. So we are considering A to be non-zero. I mean, A equal to 0 is just a trivial point when the amplitude really vanishes. So we will not consider A equal to 0. So now the next step usually how you derive. So I will just show you the final result, because it's a big derivation. But the way to derive is that you basically write dispersion relation on each of these analytic manifolds in z variable, of course. And in writing this dispersion relation, you take care of all other all the analyticity considerations that we have already discussed. And in particular, that analytic manifold, for this value of A, those analytic manifolds actually fall within the axiomatic domain of the amplitude. And the final result looks like this. So alpha naught is basically a subtraction constant. Now this subtraction is actually this subtraction is a manifestation of the original two subtraction dispersion relation. In fact, because the fixed transfer dispersion relations were two subtracted, it will induce an associated subtraction policy for z dispersion relationship, which will ultimately manifest into presence of this alpha naught. Now the kernel of the integral transform, which is the H, this is clearly now manifestly crossing symmetric under S1, S2, and S3.
Hi, Parthiv. So
yeah,
there's only one constant which shows up?
Yes. There's only one constant.
Even when there are two subtractions?
Yeah, but because the way it comes, because when you write the two subtraction in the usual case, that's in the fixed transfer dispersion relationship, you get the two constraints. But the way it is packaged, because it starts, the way it is packaged in that terms of the z variable, especially the crossing symmetry, it actually gets rid of this extra parts, and you are left with this.
So there's a simple way to understand this. So you see, if you have two subtractions, then you will have an ambiguity in the constant and the ambiguity in the linear part. But the linear part satisfies s plus t plus e equal to 4m square. So that again becomes a constant. So that's why the whole thing is just a single constant. Did you did that make sense, Akhil?
Kind of. What I'm confused is like, so if you in this way of writing it, there's no difference between what is lost in a once subtracted and twice subtracted amplitude.
No. So this is fully crossing symmetric. So if you had looked at situations where it was not fully crossing symmetric, you would see the existence of the other subtraction constant that you have in mind. What I'm saying is that
I mean, the other
you
subtraction constant should still show up with the forum square times that value, right? Even if you add them up.
Yeah, that's the point. So it is a0 plus a1 times s plus t plus u. But what is s plus t plus u? S plus t plus u is just 4m square. So you just combine that with the a0 and call it a single constant.
Okay. So essentially, the both. I mean, it's just absorbed into this a0. Okay.
That's right. Yes.
This technology also works for massless external particles with massless exchanges.
No, if you are considering that in effective field theories, yes. I mean, otherwise it is difficult because the cuts are going to join up.
Right. So, yeah. Okay. In weakly coupled effective field theories, let's say.
Yes.
Then it works. Okay.
Yeah, but I think from even a point of rigor, I would say that it's because whatever the analyticity domains you are talking about, those for external massless, I mean, in absence of mass gap, I mean, that's not known. So yeah, if you assume Mandelstam analyticity, you are free to do. I mean, you may be able to do it.
Okay.
Can I ask one more question? In this parametrization, there's also a k, right? When you define the manifold, was that a real parameter of this parametrization?
Oh yeah. No. So the k actually in the process, the k actually gets restricted in terms of a actually, not just that.
Thanks.
Because that's because again you can see that it's again because of the fact that essentially you have two variables to work with. Okay. So right. So this is the dispersion relation that we are going to work with. Right. So the amplitude, which is a crossing symmetric function, which can be expanded in two ways. Which is okay. First of all, since x, y, which were just as I recall that x was s1, s2 minus plus s1 plus and y was s1, s2, s3. Now, as you know that x, so this one and then plus s plus 2, 3. These three are elementary symmetric polynomials, so a symmetric function should be power expanded in them. And plus, but since the constraint is that s1 plus s2 plus s3 is a constant, so essentially, ultimately, it comes out to be a function of. It should be able to be power expanded in these two variables. That's why you can write it down as a Taylor expansion, expanding about x equal to 0, y equal to 0. But you can express obvious.
One question. So the usual type of dispersion relation is nice in the sense that the partial wave unitarity is very clear. How the imposition of that partial wave unitarity is just straightforward. So here also you will talk about how to impose.
Yes. Yeah. I will talk about the partial wave unitarity. How it. So the script W sub P and Q's are the Wilson coefficients essentially. So they are the coefficients that appear in the low energy expansion of the amplitude. Now this amplitude can also be expanded in the crossing symmetric variable z tilde, which is basically the z cube, because it turns out that the z cube was the fully crossing symmetric variable. So you should be able to. It should be a function of z cube, and of course as a function of a. So it's in this form where we, the story of mathematical story of univalence will enter.
Can you please show the explicit correspondence between these two series?
Yes. Yeah. So so what you're asking is the relationship between this script W and alpha, right?
Yes.
Yeah, that's what I'm showing the next. So these can be related, by this relationship. So where this is, on this side you have alpha p a times a to the power 2p, and it's related to this as a linear sum over the Wilson coefficients. So this is in general, it's a polynomial. In general, it's a Laurent polynomial in A. So I mean, in general, so alpha p. That means you can see that there can be negative powers of A that can creep in the structure of the expression of APA. And so what our goal will be, or how the problem will be approaching, that the bounds will be put on directly. The bounds will be put on this quantity, and thereby, by virtue of that will translate into bound on this Wilson coefficient. So this is the main strategy to exploit the mathematical technique of the univalence function for that matter. Okay.
Hi, Parthiv.
Yeah.
Do you guys know like an integral transform way or something of capturing this?
Sorry, what?
As in, like, is there a transformation way of writing this? Like,
I mean, you want to so some kind of integral transform
of some generating function of the coefficients or something? Yeah.
No. I think I know.
There is an explicit map between the variables, right? A and Z and X, Y.
Yeah. No, I think he's so Akhil, are you asking that whether I can write alpha p as in some integral over this W times something like that?
Yeah.
No, that's not known. As far as I know, that's not known.
Okay, thanks.
Okay, similarly, H can also, so the kernel can also be expanded because kernel is fully crossing symmetric. So that can be also expanded in as a power series in this Z tilde or Z cube. And these coefficients which are beta n. Now, of course, you can explicitly work out beta n, which is a long expression. But important point is that this beta, again, another important part of this story is that this beta n and alpha n are related by what you can call an inversion formula, which is essentially what I think Akhil was something like similar, an integral transform kind of stuff. Now, this will be very important. And so just to mention that this is the usual, the usual absorptive part of the amplitude in the S1 channel or something. But anyhow, it's getting integrated into this thing. So this expression will again be of central importance to us. Okay. So far we have talked about analytic structures, but we have not. So I've not told you I think the most important part that should enter, which is the unitarity. What is the unitarity constraint and how does that manifest? So unitarity manifests itself in the form of a positivity property. So which I'm calling positivity lemma. So the statement is that for A, which is again in that regime, that minus 2 mu and 2 mu 3, which we are going to call analytic domain, in the sense that for where there is no branch cut within the disk. The absorptive part is actually positive, non-negative. So, and this is actually for S1 over the cut. This is actually easy to prove, just to show something like that. So you can write down the alpha the absorptive part as so these are your S1. So these are these ALs are essentially the imaginary part of the corresponding AL, which is the usual partial wave coefficient. So which are the usual partial wave coefficients which enter in the partial wave expansion of the amplitude. Times, of course, there's a PL. I mean, this is the Gegenbauer. And there is a normalization factor phi. So unitarity actually manifests itself in the form that this AL S1, this turns out to be non-negative for S1 2 mu by 3. Also in the given range of A and S, if you calculate this PL also is positive. So that's of paramount importance. It's extremely important. And this is positive anyway. So when you put them all together, you finally get that your AS1 is non-negative for non-negative because AL can be 0. So that's why you allow the possibility of 0. But I think what Abhijit was asking, that the important constraint of unitarity now enters here through this positivity condition on ALs, which ultimately transfers to positivity of AS1. So this will be
the Gegenbauer polynomials are positive precisely in the unphysical region, right?
Yes,
cos theta
yes,
is greater than 1.
Right.
That is the region of relevance for you here?
Right. In fact, that is the region for relevance for me. Because when you put S1 and the A, so there is a value of A, and when you translate that A into, so the argument that enters here, when you translate that in this argument, that actually comes out to be the positive. Now, and that is also why maybe it is important to mention that this sum also converges. So this is within the domain of analyticity of this script A as well. So the sum also converges, so that there is no convergence issue as well. So you can really talk about this positivity. Okay. So this is so that kind of sets the stage of how do you proceed. So the central message is that so we have cast the scattering amplitude from a function of S1, S2 or STU to a function of essentially the Z tilde. Now what we're going to exploit is that the properties of certain class of functions on unit disk that leads to interesting bounds on physical quantities like the amplitude or Wilson coefficients, etc., etc. So essentially, yeah.
Can I ask you a question? I mean, there was a certain kernel that you expanded as a Taylor series around 0 in a disk, right? So
yes.
How can you justify this, that this is actually true, really? That this expansion is true and there are no other singularities or whatever?
So you are trying to say that what is the convergence issue of this H?
I mean, why is this a power series necessarily? I mean, H is some holomorphic function in a disk or something, right? Or,
right.
Then,
so no. So yes. So okay. H can actually be okay. I did not write. Right. So okay. I can show you. So I have written this H. I can maybe write here actually. So so H actually has a very specific form, which is which can be written in this form, which is
Actually, rather than presenting it like this, you can just focus on the Z tilde dependence. So Z tilde is just simply a Mobius transformation of the Kobe. I mean, maybe that is easier.
No, but yeah. So yeah, so can be still written in this form. So so this is like 1 minus and there's some factor which is 27 is squared by S1 cube. Yeah, so it can be expressed in this form where this KZ bars are this so-called what they call Kobe functions. Now Kobe functions are known to be univalent in the unit disk. So and this is this essentially is a Mobius transform of the Kobe function. And and since Mobius transform preserves analyticity, so this will be again be an analytic function on in the unit disk. It's not only and that's how you know that this power series is
So we know Spenta, the answer to your question is that we know the explicit form, and the range of A is such that there are no singularities inside the unit disk. It's very easy to verify that.
Okay.
That is
that answers the question. Right. Thank you. Next.
Okay. So right. So let me just go to quickly the necessary math that we require to set up finally the problem. So the mathematical functions that we're interested in are the so-called univalent functions. So a function, which is essentially a complex function, is univalent on some domain. And by domain, we here mean open simply connected set of the C, complex plane. If it is analytic and injective is essentially mean one-to-one on the domain. So just to refresh the memory, the definition of injectivity means that if 2 points are not equal, their functional values are also not going to be equal. Or equivalently, if 2 functional values are equal, then that means they are evaluated at the same point. So this thing. So univalent, a function is locally univalent at some point. Locally univalent meaning it's a univalent at some neighborhood of a point z0. If the first derivative is non-vanishing, that you can show that it follows from a theorem called Rouché's theorem, that if the first derivative is non-vanishing, then it's a local univalent. But local univalence does not guarantee global univalence, in the sense that even if a function is locally univalent at every point of the domain, that does not necessarily mean that the function can be globally univalent over the domain. So one simple example is this fz equal to e to the power z, and you consider the domain to be simply a disk of radius small r, but just take r greater than pi, and you will find out that this is its first derivative is non-vanishing at each point of the domain. But it's not globally univalent because there are 2 points, which is which is plus minus pi, where these actually take the same value. So global univalence, in fact, finding the global univalence, the condition, that's the difficult question altogether. It may not be that necessarily. It's a difficult problem, and for that matter. But suppose you have and you know some way to know that something is a global univalent function over some domain, then you have some very interesting bounding properties that this function satisfies. So so we are going to consider a class of functions which is univalent on unit disk, which is normalized such that its first derivative, you can always normalize because its first derivative is non-vanishing, you can divide any function on unit disk, univalent function by its first derivative, so that it's normalized in this power series form. Now, as for the, in general, the study of also the univalent function, at least univalent function on simply connected domains. The function, this class, studying functions on this class is sufficient because you can map the unit disk to any. You can map any simply connected domain to a unit disk via a conformal map. So one prime example of this function, this kind of function, is what is called a Kobe function, which forms like this. So kz equal to z by 1 minus z whole square, which has the very simple Taylor expansion where each coefficient becomes exactly equal to the p. So bp is equal to p. Now, there exists bounds on the Taylor coefficients bp, as well as the modulus of such functions. So just to make connection with the physics, because I don't want to lose the connection, that these bounds on Taylor coefficients, which ultimately will give bounds on the Wilson coefficients, and the bound on the modulus will give two-sided bounds on the amplitude. So there will be a lower bound and then there will be an upper bound. So just to start with, there's a theorem called Kobe growth theorem, which essentially gives two-sided bounds on the modulus of the of a univalent function normalized in that way, which is of this form. Now the equality is satisfied if fz is related to Kobe function, which is of this form. This is also called a rotation of Kobe function, I mean rotation of a function essentially. So this will give you a bound on amplitude. And then there is the famous, I mean, the title, the title, which is the Bieberbach conjecture, or which is now called the Branges theorem, because it was proved in full generality in 1985 by Branges, that for f belonging to that class S and with the power series expansion as we did it, then this modulus of the stellar coefficient Bn, that is bounded by the n itself for all n greater than or equal to 2. Again, the equality holds if f is a rotation of Kobe function. So in this sense, Kobe functions are like extremal functions in the class S, because they satisfy, they become just to be the extremal functions of these bounding relations. Not just Bieberbach conjecture, but there are many other such bounding theorems and relations for which Kobe functions are actually extremal functions. So this is all the math that we are going to use in our the subsequent obtaining the bounds on the Wilson coefficients. So is there any question before? Okay, if not, then now we go to the actual problem of how can we bound the Wilson coefficients. So we start with a relationship that was there. So this alpha p where the so they are the Taylor coefficients for so they are the Taylor coefficients in the expansion of z tilde and a, and they were related by related to the Wilson coefficients via this relationship. So now the univalence, we are going to exploit the properties of univalence to put bounds on this alpha p, and that will finally translate a bound on this Wilson coefficient. So the central bound so the central result for this section is this, that this alpha n times a to the power 2n, they are bounded by n times alpha 1a by a square. So you cannot get a bound on as such alpha 1. Obviously we will see that you still get a certain information about alpha 1, but all others alpha n's, or rather are bounded with respect to alpha 1. So the ratios of alpha n by alpha 1 is and supplemented by it is to the power 2n by a square is bounded by n. Again, for this value of a, for which we are going to. So just to sketch the proof, so the proof starts with the looking at the kernel. So looking at the kernel. So this kernel is actually univalent on the unit disk z tilde less than 1 for these values of a and s1. And this goes, which I told that this actually turns out to be a Mobius transformation of the Kobe function. Now, Kobe function is univalent on the unit disk, and Mobius transformation being a biholomorphic function do not change the nature of the univalence. I mean, most importantly, it does not change the nature of injectivity. Therefore, H is also a univalent function on the unit disk. And just to say, so this beta 1 is the first derivative at origin of H, and which is actually has a very definite sign, which is strictly negative for the given range of A and S1. So then you are directly applying the Branges theorem to these betas, which just tell that beta n by beta n is bounded, beta n by beta 1. Why you're dividing by beta 1? Because H is not you have to fix H is not of the normalization for which the theorem is valid. So you have to divide H by beta 1 to get into the normalization. And with that normalization, yeah.
Can you say what is the significance of the range of A physically, for which this is valid, if there is any significance? You had some
physical
2 mu something, right? Yeah, if you go back to the previous.
Yes. Yeah, right. Yeah.
Minus 2 mu by 9, etc. Where are these numbers coming? What are they?
Oh, sorry. Okay. So order way. I mean, so mu is your 4m square. So it's like some 16m square by 9. So that's. But I mean, significance in the sense that why we are considering in this region that you're asking. Is it?
Yeah. Is there some convergence or something, or some analyticity valid only in
yeah.
this?
Yes. Yeah. So essentially this range comes from the fact that when A is in this range, and this is that I told that when you do that map from S1, S2, S2 to ZA, when A is this range, there is no cut within the unit disk. So the entire unit disk is just, I mean, so the cuts do not, the physical cuts do not map within the unit disk. If A is outside this range, it so happens that the physical cut will actually map within, along the real Z within the unit disk. Now, if that happens, then you are not, because then you essentially have to cut out that cut, and you are not going to be able to apply these theorems. And I mean, these.
Sorry, I thought the cut is always on the arc, right? Or is it not true?
No. The cut is not always on the arc. I mean, the position of the cut actually depends on the range of A. I mean, how what is the range of it?
Okay.
So, yeah.
So sorry.
Yeah.
This range of A, therefore, like, is there? Can I think of it in terms of like the Mandelstam invariance, the original variables that you started out with? Like, is it some restriction on ST and U, like S greater than 4m square?
Yes, you can. Yeah, right. Yes, you can actually invert. I mean, you can try to invert the A in terms of those in the original STU. I mean, it will be a complicated expression. That's why I did not. But important point is that, and what is important to think that if I do the opposite, I think the opposite is doing easier. Like kind of, and if you know the A, then what will be the STU variable? That's actually a little bit easier. And when you do that, that region always falls within the domain of analyticity that has been established. So that's, I mean, these. So if you look at a single channel, for example, let's say S channel, then obviously it will fall. It will, for physical S you have already taken. I mean, you are considering on the physical S, but the T values will definitely lie within what is known as a large Martha-Liman ellipse, which is the proved domain of analyticity for such an amplitude.
Okay.
Yeah.
Does it cover the whole ellipse, or is it somehow maximal?
No, within the whole ellipse. Oh, so you're asking that whether the A, the A covers the entire ellipse. That's what you're asking.
Yeah, somehow is it like optimized this range?
No. This is that. So the check is that, of course, we did. So you have to understand the logic of A being around, being in this range is that it is in this, when A is in this range, there will be no cut within the interior of the disk. But you may ask this question that, okay, but that's a point of parametrization. But you would also like to ask that whether the corresponding STU they do fall on the domain. So that's what this thing, that those things do fall within the Liman ellipse. They do not necessarily cover the Liman ellipse.
So now, Akhil's question was that this range of A that we are using, does it cover the entire Liman?
No.
The large.
No,
so the answer is no.
not,
So it's a smaller.
Yeah.
The Liman-Martin ellipse is a bigger, allows for bigger range of A.
Yeah.
And just to sort of go ahead, and maybe this is something to keep in mind, just to give away, is that the how big the Wilson coefficients can get is actually inversely proportional to the how big the range of A is. So you actually, to allow for a very sort of very large range of the Wilson coefficients, you want a very tiny range of A. So just keep that in mind. I think that might help in putting things in perspective.
Okay. Yeah. Right. So the betas are bounded by this way, and now you can bound alpha in exploiting the inversion formula. So from this, so here in the inversion formula, this absorptive part is positive that we have shown before. I mean, that comes out of the unitarity. The beta one is negative over the range. So essentially, because this is non-negative and this is negative, so it comes out that alpha one will have a definite sign which is negative, and this actually gives one bound on Wilson coefficients. But most importantly, that this is not equal to 0. So that means it's not equal to 0. Now you can consider the same equation for alpha n, and you start with this expression. And here I have just applied the usual triangle inequality. Assuming that everything is convergent, that's why I can push the within inside. And now beta n is bounded by beta 1 n times beta 1 via the univalence of the kernel. And because beta 1 is negative, beta 1 mod of beta 1 is equal to essentially minus of beta 1. And when you put this thing together, it ultimately becomes mod of n times mod of alpha 1. So essentially, you found the bound, which is the desired bound that you are obtaining for, which is alpha n by 8 square. So this is the central result that you obtain this thing. Now, this
one
result
question,
is
Parthiv.
yeah.
Sorry, if you go back to the previous page, here you are using these things on beta n and so on, but you actually know beta n as a function, right?
Yes.
So why can't you just estimate the integral by the maximum value it takes for a given value of a, and that estimation could be better than this, right? I mean, you cannot get a better estimate than that.
Yes, you're right.
Some function that you're integrating
Right.
against a, then you can just write an inequality saying that must be less than that unknown function being integrated multiplied by the maximum of that function. So would that not be better, or does it turn out to be what you wrote?
It turns out to be what we wrote. And in fact, there is a nicer story. I think Parthiv is going to mention in the end. That is the lower end of the bound can be made stronger. So whatever we are going to use, the Bieberbach or the Bieberbach-Rogowsinski bounds, are the optimum bounds. I mean, you can actually do what you just now said. You can make up a bunch of plots for beta n, and you will find that indeed the Bieberbach or the Bieberbach-Rogowsinski are the optimum ones.
I see. But beta n is kind of a simple enough function, right? So you can determine the maximum.
Yes, we can determine beta n, but beta n actually looks, I mean, somewhat similar to these Chebyshev polynomials. I mean, there are these representations where you have the square roots raised to some power minus square roots raised to some power. So it looks a little hideous. I mean, it's not something that you can just stare at and look at.
You cannot find the maximum just by imposing derivative, vanishing, and so on.
It's very complicated that way. Yeah, so it's quite complicated that way. Yeah.
Okay, thanks.
Yeah, okay. So here are some of the tests that you can, I mean, it's just, so some amplitudes which have been, for which these bounds were actually tested. So this shows the, 1 loop 5/4 amplitude, and this is like the tree-level type to string amplitude, where you have essentially deducted the massless pole. I mean, this plot, from the plotting, there is something interesting that even if we could prove, I mean, this entire proof was tightly for that range of A that we mentioned, but it turns out, at least from the plot, it seems that this bound is actually valid for a slightly higher range of A. So that but obviously we could not prove it for those higher ranges of A. Like, how do we? Because the arguments will not just work in those ranges. But that's an observation to keep in mind. So starting from those results, we can bound the Wilson coefficients. So the first bound that you can get on this, the ratio of this WZ1 by 10, this simply follows from the sign definiteness of this alpha 1. So this is the negative sign definiteness of the alpha 1. The lower bound, it turns out that the lower bound is not new, which was obtained before this paper by Ananda and Anvilla. But the upper bound is the new one, which we obtained. Now you can, for higher order Wilson coefficient, you can use the alpha p in this fashion. So, for example, for p equal to 2, this this essentially comes out like this, and then you can use obviously the bound which is obtained, and employing that bound, it will lead actually to two-sided bounds on these ratios, like W0 to essentially these ratios on things, and so that's how you can bound. And these bounds, of course, in our work we did not have bounds, but they are recently obtained by this paper by Ananda and Prashant.
Sorry, in the inequality that you proved, that it was dependent on A, but in the where did the information about A go in this? Right.
Yeah. So the A goes actually. So when you write down this, so let me just write down the expression here for quick. So your alpha 1 turns out to be something like this. So this is now you put. So this you can see that
that alpha is A. Parthiv, that alpha is A. What you've written inside the bracket, that should be A.
Yeah. And this has been proved from prior that this is positive. Sorry. This is positive. So then that would mean that that would mean that would So then you get the bound on this ratio in terms of A, but now you know that A already has a range and that's how you get these two sides.
And also like so for example, for this type of coefficients, you also have this single channel or double two channel dispersion relations by Rastelli and company, and like Simon Karen and company. Are your bounds stricter than theirs, or like
so the upper bound is actually so the upper bound is stronger than theirs actually. Okay. So right. So that's how you can numerically kind of investigate what happens with the higher bound. Now these bounds.
Can I ask a question?
Yeah.
The previous bound you said that comes from that single relation, that this A times this constant plus 1 is less than 0 or greater than 0.
Yes.
And you have a bound for A, and that's how you get these two-sided bounds.
Right.
Okay.
Hey, so do we know any amplitude which saturates the bounds, like?
So you are asking that what would happen if some amplitude?
Like some m which goes to the Kobe function or something. Yeah.
That's a very good question. So you can ask this question that whether you can turn the question in opposite way, that what would what would an amplitude would correspond if it's a Kobe function.
Yeah, like is Kobe a legit amplitude?
If so, it turns out that if you consider a Kobe function, you can get three kinds of amplitude, so to speak. One, if I right, maybe here. Yeah. So this actually corresponds to if you express in terms of x, y. So one possibility is x, another possibility is y, and another possibility is actually x squared by y. So while x, y, you can consider it to be some effective field theory, some massive effective field theory, but this turns out to be this turns out to be a gravity amplitude. So if Kobe function, so this is very interestingly that if Kobe function is indeed a amplitude, that kind of naturally gives rise to in fact that it's actually a 2 dilaton amplitude with a graviton exchange. So that's a very, very interesting thing that that this extremal function will give rise to such a gravity amplitude.
So did you say like a two dilaton scattering mediated by graviton or something such goes to Kobe? Okay.
Yeah, I mean, yeah, this is in the low expansion. Okay, so these these bounds, or at least the way the bounds look, you may be able to tempted to ask that whether before that we have the second part, which is the amplitudes themselves are bounded. So we saw just the bounds on the Wilson coefficients, but using the same principles of univalence, you can put bounds on the amplitudes itself. And that leads to two-sided bounds on the amplitude. And the theorem that we apply in order to obtain these bounds are the so-called Kobe growth theorems, if you can remember, just to, for refreshing memory. So this was of this form. So Kobe growth theorem is of this form. So and it essentially leads to two-sided bound. If you do the same thing, you can prove a similar along the same. So essentially, you go through the same technique or same line of proof as we did in the case of bounding the Wilson coefficients. That means you focus on the kernel because the kernel is univalent. So you apply the Kobe growth theorem on the kernel, and then you take advantage of the positivity in order to obtain the bound on the total full amplitude.
Can I ask a question, please?
Yeah.
This upper bound you wrote in this Kobe growth theorem. The upper bound, is it the same as the one that you get from the Pick-Schwarz lemma?
Yes. The Pick-Schwarz lemma.
Yes.
Right.
Okay.
In fact, in the Schwarz-Pick lemma, the extremal functions turns out to be the this Kobe function, if I'm not wrong.
I see. Okay. Just one more question, because sorry, I have to leave. What can you say about integrable systems of scattering amplitudes? Forget about massless particles, but take Sine-Gordon theory in 1+1 dimension as an S matrix, etc. Can these theorems be used to say something? Or is there something special that you will be able to see in an integrable system? Just a question that arose in my mind.
Yeah. No. This is actually a very good question, but I think for integrable systems, as you said, but okay, I'm not sure. So I've not seen. I'm not sure about the. Definitely there are works, but how the analytic structures will be there. I do not know, frankly speaking. So before coming to this entire thing, I would say that I would like to write a dispersion relation for. Because ultimately it's centering on the dispersion relation. So yeah, I'm not sure that how much that is because whether it's written there, like that. But yes, indeed, it will be a very good question for integrable systems, actually.
Thanks.
Yeah.
Sorry, can I ask?
Yeah.
In
Yeah.
1+1 dimension, like, can you write this dispersion relation at all, or like?
Yes. That is what I am. That is what I am
okay.
Suspecting, because because I think if I cannot remember exactly what I where, but exactly that in that 1+1 dimension you have these issues where you cannot write down dispersion relations and so on. Okay, so you can now put the same bound, and where I've just written the bound using this x variable, which is s1, s2, s3, but let's we can put it in more useful or more familiar looking. So let's look at the Regge limit, which is s1 goes to infinity, keeping s2 fixed. If you do that, in that limit, it would look like, so the upper bound will look like a mod x. And in the limit x, in the Regge limit, x goes like, it will go like s1 square. So you have the familiar, the so-called the familiar s square bound that we expect. But there's one interesting point is that there is a sine square theta by 2 sitting at the denominator, where theta is basically the phase of the S1. So you can see that for S1 real, this becomes a trivial bound, but that is not a problem, because after all, this bound was derived by considering that that our function was analytic and injective in the open disk. But when S1 becomes real, that assumption or that works actually falls flat. In fact, it turns out that the cuts again enter in along the real set. So for our
Sorry, can I ask? Like, you expect the upper bound, since you are considering quantum amplitudes to be less than s square, right? So
yes.
Why is it less than s square?
No, it is less. So you're asking that why it is less than s square?
Like I mean to say that it seems like you are getting like not the Frossa bound, or
no. I'm not getting the Frossa bound. That you are right.
So does that mean that this can be improved further? These bounds.
Okay. Yeah. I mean, I would say. At least
maybe we
not
can
from
answer this later. Yeah, sorry.
But there is also a lower bound, which is there, which interestingly, whose leading term is a constant, which is 1/4. But just to make the final point, that in order to apply this bound, you have to consider S to be not real, but some phase. And so essentially, you have to avoid the theta equal to 0 and theta equal to 2 pi. Okay. So it's just that the thing that the presence of sine square theta by 2 in denominator, the upper bound would be trivial for real S1. But that's not a problem, because real S1 really gets mapped to the boundary of the disk. And the boundary of the disk, that is on the unit circle. And there, these, of course, the theorems are not valid. So finally, one question that you can ask, that whether the scattering amplitude itself is univalent. That's obviously a very important and valid question, because the bounds, the various bounds kind of look like, as if you may be tempted to kind of go bold and kind of conjecture that, okay, whether it is possible the scattering amplitude is univalent or not. The amplitude actually turns out to be a convex sum of univalent functions, because the amplitude looks like there's this kernel which is univalent, we showed, times some function which is positive. So essentially, it's a convex sum of univalent functions. So, but unfortunately, as for the convex sum of univalent functions, whether it's in what domain it will be univalent function, we could not. It's not known to us right now that what are some firm statements about the possible status of univalence for convex sum of univalent functions. So that's I would say it's a not well established. However, it was pointed out. It was there already, but it was kind of rekindled that amplitudes are a special class of functions which is called typical real function. So a typical real function is nothing but that it's just which just satisfies this property, which really means that in the upper half plane the function has positive imaginary part, in the lower half plane the function has negative imaginary part. Now it so happened that the way it goes, like the kernel itself is a typical real function, but the convex sum of typical real functions is known to be typical real functions, and that's how you know for sure that the amplitude is going to be typical real function. And typically real functions also satisfy bounds, and even in fact, for typical real functions, Bieberbach conjecture was proved by Rogozhinsky long back in 1931. And in fact, you get this Bieberbach Rogozhinsky kind of bounds, and there are also stronger bounds available for typical real functions, which you can put to use in this context to get more, bound. Can actually give rise to improved bounds on the various aspects.
So, Parthiv, sorry. Maybe you can finish the sentence.
So you can use those properties further to explore more constraining bounds on Wilson coefficients and the amplitude. Yeah, please go ahead.
No, I was just saying that explicitly the S matrix is for integrable theories, as Penta was referring to the integrable theories.
Yes.
And you have this function in front of you, and then you can just see whether it's Bieberbach or not, whether it's univalent or not, right? Presumably not.
Yes. Oh, yeah. I can always make that.
You can just look at that function.
Yes. Yeah.
So
yeah. In fact, I can just blindly put the parameterization into the place and see that whether it's just
just plot the function, see whether they take the equal values or something.
Right. So
yes. So what is a priori a reason to even expect that such a thing could be true, or why should one ask that in what conditions it should be true? Because as you say, convex sum seems to spoil this property quite dramatically, right? So why should so
the convex sum for typically real is still typically real. So I think the univalence property is
this univalence thing.
Yeah, so univalence is not going to hold, but typically real is going to hold.
Okay.
So I think maybe I can say that the property of typically real is also called Herglotz in mathematical physics. And this was actually first introduced in physics or studied in physics by Wigner in 1951. And he was studying scattering. And in fact, from the perspective of a simple Schrodinger equation, you can actually write down what are called R functions. And the scattering amplitude he was studying nuclear physics. He was studying slow-moving neutron scattering of a nucleus. And he introduced these R functions, which are typically real, or Herglotz or whatever. And so there is reason in physics to study these functions, except that nobody seems to have not too many people have studied it in the context of say bounding Wilson coefficients like what we have done.
I see. Okay, thanks.
Okay. So with this, let me just finish up towards my end. So let me just give you some outlooks. So there are many avenues to explore. I think one of the thing that you can out of this entire study, apart from obviously the practical aspect of bounding amplitudes and bounds, on a much more philosophical level, because this entire discussion incorporates crossing symmetry in a rather natural way. So you can ask this question that, can one replace the requirement of locality, analyticity, which is again a consequence of causality, or unitarity by some kind of single property like univalence, maybe not single, but maybe multiple, or typical realness, or perhaps some even stronger property, some stronger mathematical property. Or maybe you supplement, you just if not replace, at least you can supplement certain aspects of these properties with such a single property, something like that. So that's a much more philosophical, at a philosophical level, it would be a reformulation of the physical principle. And that you can ask this question that whether it can be promoted to such properties can be promoted to a status of a physical property, a physical principle. On a more practical level, you can ask this question about how to take care of the bound states. So obviously here we did not consider bound states into the picture. That means we did not look into poles, we just the cuts. But suppose we allow for bound states, and how do we handle the bound states properly? How does the various bounds change in the presence of bound states? So essentially, presence of bound states meaning you are meromorphic and you are essentially not maybe in the univalence in the disk. But mathematicians have studied properties of univalent function defined on an annular domain, even on like punctured disk. So how we can employ those techniques to this context? What about, and a very natural question would be that what about the external spinning particles? Very recently, there is a work which explores the 4-photon amplitude from usual fixed transfer dispersion relationship. It would be very interesting to explore our technology in these contexts. And in particular, from a more practical point of view, what can be said, for example, for standard model effective field theories? How do we apply these things in the context of standard model effective field theories? For example, in effective QT Lagrangian, like Euler-Heisenberg Lagrangians, and so on and so forth. Recently, there is the connections between this gravitational wave physics and effective field theories are being pointed out for quite some years and being explored. So one can wonder that whether our technology or our way of seeing effective field theory amplitudes will have any imprint in the gravitational wave physics. In particular, whether we can see in the properties of the gravitational waves, we are going to whether we can bound some classical observables using such quantum bounds. So to end the note, let me quote following from a paper by Jean Martin, which basically tells that even they told that one may of course feel disappointed that these general requirements on scattering amplitude lead to rather weak conditions, most of which everybody was prepared to believe without proof. However, it seems to us that to be necessary task to explore bit by bit the rigorous consequences of analyticity, unitarity, and crossing. Who knows if someday one will not be able to resemble the pieces of puzzles. So clearly our ancestors had the hints that such techniques are indeed of use, but obviously they could not go ahead much. But today we can definitely prod away and ahead with some fresh outlooks and maybe come up with some new ideas. Thank you.
Thank you very much, Parthiv, for a wonderful talk. Let's all unmute and applaud. Okay. We have more questions for the speaker.
Hi, I have a question. So, how much of this kind of crossing symmetric approach seems to be generalizable to say higher point? How much of this crossing symmetric approach can you generalize to say higher point?
Sorry, I can't hear you.
Okay.
Hello, can you hear me? I could hear Akhil. Hello.
Hi.
No, I think Parthiv is not able to hear.
Parthiv is not able to hear. Yeah. Hey, Parthiv.
Hello.
Can you hear us?
Sorry, I can't hear you guys. Or maybe that's a problem.
Oh, suddenly have you?
What just happened?
Yeah, we can hear. Yeah, okay. I guess he's not hearing, so I'll just chat.
But Akhil's question is very good. I mean, it's a very interesting question that higher point functions, can they, in some special kinematical configurations, can they give us more information than what the 4-point function gives us? And it's very likely, except
I can't hear you.
Sorry, who can't hear? Who said that?
Parthiv, probably.
Okay, but this thing, I think the technical challenge there is that the number of these variables will number of Mandelstam variables or number of crossing symmetric ratios in the context of conformal field theories will be a lot higher, and so you might have to take slices. You have to take various slices, clever slices, and see whether you can extract extra additional information or not. So in that sense, it might be an interesting question to pursue, but nothing has done. Nothing, so far as my knowledge is concerned, nothing exists.
Naively, it seems this parametrization can be generalized, right? Like you could take n-point cube roots, n-point roots, and put a cut disk and all that.
Yeah, absolutely. I think there will be some generalization of rather than cube roots and nth root of unity or something like that. I think definitely something like that will exist.
May I ask a naive question? Like, so you guys are discussing also whether you should expect the amplitudes to be univalent, but if I tune for some, like by hand tune some theory with some attractive and repulsive kind of mediators, shouldn't at least at some kinematic points I have the derivative of amplitude to vanish? Isn't that possible?
I'm not sure I understood that question. So you could definitely have some bound state, intermediate bound state, but you can always choose your parametrization or choose the values of A such that the bound state gets mapped to the boundary. So you can still apply these Bieberbach Rogosinski within the disk. So the most important thing is to have a disk where your function is analytic. So that is the first and foremost requirement. The second requirement is that if you do have a bound state, you can try to find a range of this extra parameter that we have at our disposal A to map this bound state to the boundary. If you can't do that, so for example, suppose there is some reason why you cannot move the bound state to the boundary, what you can try to do is there are these Bieberbach Rogosinski inequalities that have been generalized to the punctured disk or even the annulus. So then you can actually start sort of saying that, okay, we will allow for these singularities within a certain radius of the disk or within, say, at the origin, and then we want to see what happens to the bounds. So there are a lot of mathematical things that are known about these things.
No, I was wondering if, like, I mean, it's you also want it to be univalent, right? The whole amplitude to be univalent in the disk.
Well, univalent or typically real. I think typically real is a better requirement, or
I see.
It's a weaker requirement. Yes.
I see. Yeah. I was just wondering if you can cook up the amplitude to have vanishing derivative at least once at one point in the interior or something of the disk.
That Parthiv will know. I mean, maybe.
No. Okay. If you have a vanishing derivative, that would, I mean, the moment you have a vanishing derivative at one point, that would break down the univalence. So the necessary, so see, if you want to have a global univalence, you have to have local univalence at all the points. And the necessary and sufficient condition for local univalence would be to non-vanishing derivative.
Yeah, so
I think Akhil is asking that why can't we cook up an amplitude where the first derivative vanishes? So that would actually be a counter example to a possibility that there could be the amplitude itself could be univalent.
Univalent. Oh, yeah, but I mean, that seems to be, I mean, cooking up, I mean, that seems to be extremely, because there's a lot of other things that enter into, like,
that's why
say at some tree level. Sorry. So, go on.
Sorry, no, that's why I specifically said integrable models, right? You know the full thing there. Then you can just see whether it's there.
Yeah, that's worth studying actually. I think, yeah, that's a great question. I think we should examine that. Yeah.
By the way, one question.
Yes.
So this is also to you, Anindya. So this crossing symmetric dispersion relation kind of reminds me of this Polyakov-Mellin bootstrap also, where you kind of put the crossing symmetry first, and by
that was a motivation for looking into that.
Yeah, I would imagine. So, yeah. So if I think about it that way, in that context, the non-triviality then manifested as the absence of spurious singularities, right?
Yes.
So in this case, what is the analog of that? When you write it in this way, in this crossing symmetric way, what is the bootstrap constraint, let's say?
There are two very interesting and very important questions there. So let me just. So one thing that Parthiv probably did not emphasize enough is that so in the fixed dispersion relation, you impose crossing symmetry by hand. So you seem to have extra conditions. So what are the analogs of those conditions in our in this crossing symmetric approach? So one thing is that in the crossing symmetric approach, the penalty that we are paying to maintain crossing symmetry is that we are losing manifest locality. So in principle, you could have negative powers of x. So x was the quadratic invariant in Mandelstam. So you will start getting them these negative powers in the you start getting quadratic invariant in the denominator, and that is something that you that is not desirable. So so you want to in a local theory you cannot have these. So that is the analog of those constraints. The second question that you're asking is that there are these Polyakov double pole cancellation conditions in the Mellin bootstrap. So what are the analog of those in quantum field theory? So the answer to this is not completely known, but there's a conjecture by Zubodov essentially Zubodov and collaborators, I think Korea, Amit Sever and Zubodov, who say that the analog of these conditions will be like imposing the elastic unitarity constraints. So here you don't want to you want the unitarity condition, the equality, not the inequality, the equality that imaginary part of FL is equal to mod FL square, that to be satisfied in the range S between 4 and 16. So there's a conjecture that that is the condition, like the Polyakov double pole cancellation condition.
Yes. Okay, thank you. So if I were just push this question a little bit further into specifics, so I was thinking in the context of string theory, where we seem to think of Virasoro-Shapiro amplitude, for example, as some sort of a miraculous function, right? Which has certain nice analyticity properties as well as crossing symmetry. It's not something that is random. You cannot just write it down, right? But if I take this point of view of crossing symmetric dispersion relation and write down a crossing symmetric dispersion relation form of it, where is going to be the constraint? I guess presumably the constraint is going to come on the analytics. I don't know. So where is, from that point of view, it doesn't seem that it is so.
Yeah, so it is a great question. So in fact, so there are these alternative representations for these are ratios of gamma functions. So there are these alternative representations which have not been properly studied, I think, in the math literature, which looks like, so we presented this, an explicit formula in the paper that I wrote with Ahmadullah, where you have this crossing symmetric expansion of the Veneziano amplitude or Virasoro-Shapiro amplitude. You can do those things. The thing is that if you suppose you started off by saying that I'm going to write down an amplitude which has got an infinite number of poles, but I am going to maintain crossing symmetry, okay, and I want a certain range of A. It cannot be just a single value of A where this is maintained, some range of A. Then I think you will be forced to impose the conditions are going to be, the non-trivial conditions are going to be that you're imposing locality. So where is the information of locality going into all this? So you cannot have negative powers of x like what I said. The dispersion relation allows for these negative powers of x. A general theory, a general crossing symmetry dispersion relation would be non-local. So I think locality is what.
So where is this negative power of x? Because I remember the discussion relation was this integral ds prime something with an with a kernel which is simple enough, and then the discontinuity. Now where exactly the x that
exactly. So the absorptive part. The absorptive part is where the possibility of negative powers of A comes in. So you see, in the fixed T dispersion relation, the absorptive part is just a function of the integration variable S prime and T. In this particular case, T is constrained because it satisfies this parametric condition that y by x is equal to A, right? And so that actually gives you a quadratic equation for T. So that is why if Parthiv can go back to that explicit form, you will see that there is an S2 plus that is sitting in the dispersion relation, in the absorptive part of the dispersion relation. So yes, this one.
Okay.
So you see the argument is S2 plus, and S2 plus is this function here. Okay. And now, if you remember that the domain of A actually allows you to Taylor expand around A equal to 0. Okay, so if you Taylor expand around a equal to 0, that would mean that each partial wave in principle can have an infinite number of polynomials, monomials in A. So A to the power 25, A to the power 26, whatever. Okay, so and A was Y divided by X. So that means that for a fixed block, a fixed spin, you can have any negative power of X. It is only when you sum over all these spins, or when you sum over all these blocks, that these negative powers of X will cancel. So that is the take-home message, that block-wise, and these guys, in order to maintain good Regge behavior, so to speak, they have to be non-local. They have to allow for negative powers of X. Okay, but when you actually sum over all the blocks, these negative powers of X will go away, and we have checked that explicitly. That is exactly what happens.
I see. For string theory also.
Yes, for string theory also. I mean, for the 2-to-2 real Jones scattering amplitude. Yes.
I see. Okay. Yeah, thanks. Quite useful. Any more questions? If not, let's thank Parthiv again for really nice talk and answering all the questions so patiently.